Bismillahirrahmanirrahim. Assalamualaikum and hi everyone. I hope all of you stay safe and stay at home during this MCO period. Let's restart our class now. Chapter 5 Symmetrical Components. At the end of this chapter, students should be able to explain the importance of symmetrical component, construct positive sequence, negative sequence, and zero sequence networks for a power system. Symmetrical component method was introduced by C.L. Fortescue in 1918. This method allows unbalanced three-phase phasor quantities to be replaced by the sum of three separate but balanced symmetrical components. This technique is applicable to current and voltage analysis, and it permits modeling of unbalanced systems and networks. In the symmetrical component transformation, there are three different sequences that are used to represent symmetrical components, which are positive sequence, negative sequence, and zero sequence. Positive sequence and negative sequence consist of three phasors with equal magnitudes and plus minus 120 degrees phase displacement. For zero sequence, it also has three phasors with equal magnitudes, but the phase displacement is 0 degrees. Figure 1a, b, and c show a phasor diagram of current for positive sequence, negative sequence, and zero sequence. From figure 1, A, B, and C, we can see that each sequence, positive, negative, and zero sequence, has three different symmetrical components. For example, we look at the positive sequence. Positive sequence has IA1, IB1, and IC1. I stands for current, A stands for type of phase, and numbering shows the type of sequence. So 1 represent for the positive sequence, 2 represent for negative sequence, and 0 represent zero sequence. Now we proceed how to analyze the phasor diagram. We start with the positive sequence phasor diagram. Okay, as shown in figure 1a, which is positive sequence phasor diagram, we can see that this sequence has three symmetrical components of current that labeled as IA1, IB1, and IC1. Positive sequence has equal magnitudes. Therefore, the length of the arrow of this phasor diagram is equal as well. Each symmetrical component of current for this positive sequence has 120 degrees phase displacement. Okay, from the phasor diagram, we can write the symmetrical component current equation. Before we write the current equation, we need to set the reference point. Let's take IA1 as a reference point. Now we can write the symmetrical component current equations. So the equation for IA A1 equals to magnitude IA1 and phase angle is 0 degree. Why the phase angle of the IA1 is 0? It is because IA1 is reference point. Therefore, we can rewrite the equation as IA1. Next is the equation for IB1. So IB1 equals to IA1. And what is the value for the phase angle for IB1? To calculate the phase angle of IB1, we must refer to the positive sequence phasor diagram. The angle is between reference point IA1 and IB1 in counterclockwise direction. Therefore, the angle is 240 degrees. So we can write IB1 equation as magnitude IA1 with phase angle 240 degrees. Or we can rewrite this equation using the operator A identities. So the equation become A to the power of 2 times IA1. What is the operator A identities? The information of the operator A identities we can refer to the next slide. Here. This is operator A identities. As we can see, A is equal to magnitude 1 with angles 120 degrees. This is, we write the value of A in polar form. So we can write the equation or the value of A in complex number as minus 0.5 plus J 0.866. A to the power of 2 is equal to magnitude 1 with 240 degrees. So how we get the value of A to the power of 2? So A to the power of 2 is equal to A times A. So A is equal to 1 with 120 degrees times 120 degrees. So we will get 1 with 240 degrees. This is for the A power of 2. The value for A to the power of 3 is equal to magnitude 1 with angles 0 degree. So how we get this value for A to the power of 3? So A to the power of 3 equals to A times A times A. So we calculate, we multiply 120 degrees and 20 degrees. So we will get 1 with angle 360 degrees, or we can write as 10 degrees. And for the last equation for operator A identities, why we get 0 here? It is because A plus A power of 2, if we calculate, we will get minus 1. So 1 plus minus 1 is equal to 0. Okay, now we continue our phasor diagrams analysis for positive sequence. As we write the IB1 equation, we use operator A identities in question here. So how we get this equation? We just refer to the previous equation simplify the equation. So substitute the value of 1 with angle 240 degrees to a power of 2. Therefore, the equation becomes a to the power of 2 times IA1. Next is equation for IC1. So IC1 is equal to same magnitude IA1, and the phase angles is, we refer to the phasor diagram where the angles is between reference point or IA1 and IC1. So the angle is 120 degree in counterclockwise direction. So the answer is 120 degrees. Or we can rewrite using the operator A identities as A, I, A1. Now, let's analyze the phasor diagrams of negative sequence. How to write the symmetrical components currents for negative sequence IA2, IB2, and IC2. From figure 1b, negative sequence phasor diagram, we can see that the position or the sequence of symmetrical component current is different if we compare to the positive sequence. The positive sequence use ABC sequence, but negative sequence use ACB sequence. So we can see that for positive sequence, the ABC is in clockwise direction, and for the negative sequence, the symmetrical component currents, ABC is anti-clockwise direction. Therefore, the equation for the symmetrical component currents of negative sequence are not equal to the positive sequence symmetrical component currents. Before we write the equation for IA2, we need to assume the reference point first. So let's say the reference point is IA2. So IA2 equation equals to IA2 is the magnitude with 0 angle, since IA2 is the reference point. So we can rewrite the equation equal to IA2. And for IB2, the magnitude is IA2, and the angle is between IA2 and IB2 in counterclockwise direction, which is 120 degrees. Or we can rewrite the equation using the operator A identities. So the equation becomes A times IA2. And the last one is IC2 equal to IA2, and the phase angle of IC2 is between IA2 and IC2 in counterclockwise direction. So the total for IC2 phase angles is 240 degrees, and the equation for IC2 is equal to a power of 2IA2. Now we proceed to the last phasor diagram, which is zero sequence phasor diagrams. Based on figure 1c, it shows that the magnitude of symmetrical component current for zero sequence is equal, but the value of the phase displacement is 0 degrees. Therefore, the equation for symmetrical component currents of zero sequence are IA0 equals to IA0 for the magnitude and 0 degrees for the angle. So we can write as a IA0, and for the IP0 is equal to IA0, also 0 degree, and we can write IA0. And the last one is IC0 equals to IA0, same phase angles, and we can write as IA0. So for the zero sequence symmetrical component current, we can conclude that IA0 equals to IB0 equals to IC0. From the positive, negative, and zero sequence symmetrical component currents that we have analyzed before, we can use all the symmetrical component equation in order to analyze the unbalanced phasor. So as we know that each unbalanced phasor has symmetrical component. For example, let's say we have current for phase A, IA. This is current for phase A. So current for phase A consists of IA0 plus IA1 plus IA2. And for phase B, this phase consists of IB0 plus IB1 plus IB2. And for phase C, the current is summation of IC0 plus IC1 plus IC2. Okay, based on this phase current equation, we can see that each phase IA, IB, and IC consists of a symmetrical component current for each sequence, which is zero sequence, positive sequence, and negative sequence. So how to analyze the unbalanced phasor if we are given the symmetrical components? To analyze the unbalanced phasor, if we are given the symmetrical components, currents or voltage, we can use or we can convert the phase current or phase voltage into the metric notation or metric form. Before we convert all this equation into the metric form or metric notation, we need to simplify all this equation into the reference phase, which is IA0, IA1, and IA2. Now we simplify the equation IA first. So IA equals to IO0. From the phasor diagram analysis for negative, positive, and zero sequence, IA0 is equal to IA0. This one we can refer to the previous analysis. We can see that IA0 equals to IA0, IB0 equals to IA0, IC0 equals to IA0. So we can refer to the previous analysis, and IA1 equals to IA1 and IA2 equals to IA2. For IB equation, IB0 is equal to IA0 plus IB1. If we refer to the previous phasor diagram analysis, we can see that IB1 is equal to A power of 2 times IA1. So A power of 2 times IA1, and IB2 is equal to A times IA2. Next is IC equation. So for IC, we can write the equation as IC0 is equal to IA0 plus IC1 equals to IA1. You can refer to the previous slide. And then IC2 plus A power of 2 IA2. So from this equation, we can convert this equation into the metric notation. So we can write in metric notation, matrix form or notation. So IA, this is a phase current, IB, IC equals to IA0, IA1, and IA2. So we can fill this matrix with 1, 1 and 1, 1 A power of 2 A, 1 A power of 2. We can refer to this equation. This is 1. This is the metric form for the phase current IE, IB and IC. This part we call as a phase current, and this one is symmetrical component current. So in order to determine the phase current, if we are given the symmetrical component current, we can use this metric form to calculate or to identify the phase current for IA, IB and IC. How about if we need to identify the symmetrical component current if given the phase current value? So we can use the same method, which is we can use the equation using the metric form. If we want to calculate or to identify the value of symmetrical component current, we can use the same method as we calculate for the phase current. We can use the same matrix equation that we developed before. So from this metric equation, rearrange or rewrite into the single line equation. So we write as I A B C equal to A times I 0 1 2. I A B C represent the phase current. A is the identity of the matrix and I0 1 2 is the symmetrical component currents. Then we rearrange the equation, move the symmetrical component current I0 1 move to the left side and IABC move to the right side. So the equation become I0 1 2 A inverse times by IABC, where the value of matrix A inverse is equal 1 over 3 and the matrix is 1 1 1 1 A power of 2 1 A power of 2 A, and this is the value for A inverse. Next, we need to expand this single equation into the matrix notation. So the matrix notation equation we can write as I A0 I A1 2 equals to inverse A times by phase current. So this is the metric equation if you want to calculate for the symmetrical component current. So from this metric equation, we can calculate for IA0, where IA0 equals to 1 over 3 times summation of phase current IA plus IB plus IC. And then from IA1 equals to 1 over 3 times IA plus A times IB plus A power of 2 IC. This is for IA1 and IA2, negative sequence symmetrical component current. IA2 equals to 1 over 3 times IA plus A power of 2 times IB plus IA times IC. So these three equations we can use to calculate the symmetrical component current. How to calculate if we are given the symmetrical component voltages? We can use this equation to identify or to determine the value of phase voltages or symmetrical component voltages. This equation is similar to the symmetrical component currents and phase current. If we have the value of voltage and current, we can calculate the apparent power, the value of real power, and also reactive power. This is the apparent power equation. So S three-phase equals to phase voltages transpose times by phase currents conjugates. So how to prove this equation? As we know, S three-phase equals to phase voltages transpose times I ABC conjugate. So VABC is equals to AV symmetrical component transpose times AI symmetrical component conjugate. So we simplify this equation. We have V012 transpose and I012 conjugate and A transpose times A conjugate. So A transpose times A conjugate equals to 3. So the equation becomes 3V012 transpose times I012 conjugate. Then we expand the equation. We get 3VA0, VA1, VA2 times transpose IA0, IA1 and IA2 conjugate. So we get VAO, VA1, VA2. We transpose the symmetrical component voltage and then times with the IAO, IA1, IA2 conjugate. And then we simplify, we get 3VAO times IAO conjugate plus VA1 IA1 conjugate plus VA2 times IA2 conjugate. So this is the equation for the apparent power three-phase. So that's all for today. If you have any question about the topic, do not hesitate to contact me, and see you in the next video. Thank you and Assalamualaikum. Bye.